Welcome to the course on principles of vibration control, and today we will be talking about dynamic vibration absorber, which is a generalized case of the vibration neutralizer or auxiliary mass damper. So, we will talk about that how to model a single degree of freedom system with dynamic vibration absorber, and then we will talk about the transmissibility and relative transmissibility of such system. And finally, also we will talk about an active dynamic vibration absorber. So, just to keep yourself tagged with the subject, if you remember, we have earlier said that suppose you have a simple spring and a mass system, and then if I add another spring and another mass, which is the secondary mass. Okay, so, this is MS secondary and this is the M primary, okay, stiffness primary, K secondary. Then this system is a special case of DVA, which is known as vibration neutralizer. Also, there is another special case possible. That special case is that you have again the primary system, and instead of a spring you have a damper here and then the secondary system. So, let us call it damping constant of the secondary system, and then this system is known as AMD or auxiliary mass damper. Now, suppose we want to mix these two things together. That means, we want to have a handle not only on stiffness, but also on damping. Then we will be getting this generalized case of DVA, in which we will be having a spring, okay, Kp, then the mass MP, and followed by, I am giving a different way of representation of it, something which is a stiffness which is complex in nature. Now, complex stiffness is equivalent to having a spring and a damper. That is something that we have to keep in mind, that K star means K real plus J K imaginary, and while K real is actually our secondary spring, the K imaginary, J K imaginary, where J is the square root of -1. So, imaginary thing, this part, the imaginary part is actually giving us the damping part. So, that is how, by denoting this secondary part as K star, we are taking care of both of such a system. Now, let us look into the DVA system. So, here we have the primary system as has been shown here, K1 is the stiffness instead of Kp, here we are denoting as K1. M1 is the mass, and then K2 star is the actually these complex stiffness, and M2 is the mass of this secondary system. Now, such a system is useful for two different types. One is called base excitation problem, where the support is getting an excitation, harmonic excitation, and another is a force excitation problem, where the primary is actually subjected to a force excitation of the system. Now, actually for many linear cases it can be shown that the transmissibility that we talk about is actually the same for both the cases. One case, this is called displacement transmissibility. So, this is displacement transmissibility. You can find out the transmissibility of such a system, and another one is called force transmissibility. In this case, it is the force transmissibility. in fact both the transmissibilities are actually very equivalent. So, if we work on either of the models, it is actually good enough to talk about the other. In order to do find out the governing equation, let us then start with one of the models. Okay. So, let us say that we are taking the first case where we are having the transmissibility as x 1 over x, where x 1 is the amplitude of vibration of m 1 and x is the amplitude of vibration of the base. So, this is a base excitation problem. Okay. And x 1 is you may also think of it in this way, that x is the input to the system and x 1 is the output response of the system. So, this is something like an output over input. Now, if I have to do the same thing for the other case, okay. So, suppose for the force transmissibility, what we would have done? The output in this case, one output could have been possibly that what is the force that is transmitted here. Okay. So, if you call it as F t. So, that F t, so in that case the force transmissibility, so the transfer function in this case would have been in the input here is F itself. So, just like here you have the input here as the x here as the amplitude of vibration of the base. So, similarly here in this case the input is the force that you are giving. So, that is F and the force that you are transmitting and an amplitude of the 2. So, that is going to give us the transfer function in this case. Now, the other case we will be just now going through. In this case also you can actually find out that what is the force which is transmitted. So, just try to find out that what is the force that is transmitted. For that you have to look into the equilibrium of first of all the mass m 1. So, m 1 if I look at it, then what are the forces working on m 1 if you look at it, then m 1 is undergoing, these are the forces that we can see, that m 1 x 1 double dot, that is your what you call the inertia force, and then you also have the k 1 x 1 minus, so that is the k 1 x 1 part itself. This is fixed of course. So, this is the k 1 x 1 part, and here you are also going to have k 2 star x 1 minus x 2, right. And of course, you have the force which is working on the system, that means it is F e raised to the power j omega t, or you can call it as F e raised to the power j omega t. So, these are the total forces that are working on the system. Now, if you look at the spring point of view, so the spring point of view, then the force that is transmitted is simply k 1 x 1, right. So, so the force that you are getting here is actually k 1 x 1, that is what is transmitted through the spring to the base. So, you can actually, by solving the governing equation of motions in this particular case, so this is one, and the other one is of course related to the m 2, you need to have both of them with you. So, for m 2 you will be having k 2 star x 2 minus x 1, that is the way it will work, right, and you will be having an inertia force, right. The inertia force is m 2 x 2 double dot. So, that is for the m 2. So, you can get a governing equation corresponding to this free body diagram. I leave it as an exercise for you, and you can get one corresponding to this, and then you should be able to find out what is the transfer function for the force transmissibility, and you will find out and you can confirm yourself that this will be equal to the displacement transmissibility of the system. Now, as far as the displacement transmissibility goes with respect to base excitation, sometimes we also use a relative transmissibility term, and in this case it is actually the denominator remains the same, but the numerator becomes the difference between the amplitude of vibration of M2 and M1, and that is instead of x1 itself, it is x2 minus x1 that comes into the picture. So, sometimes this relative transmissibility is also used in certain applications. Now, what will be the equation of motion of this system? So, in this case it is only subjected to base excitation. So, that means if we try to draw this part, if you remember what are the forces we are getting subjected to. So, M1 was undergoing so there is this is the direction of movement of M1 x1. So, that means there will be an inertia force M1 x1 double dot, that is what is our first term here. And then you also have in this case the spring K1, which is actually there is a base excitation there. So, it is K1 x1 minus x, that is what is the spring force, and also you have an additional. So, that is your second force, and also you have an additional force which is K2 star x1 minus x2, that is from the secondary system. So, that is the equation of equilibrium corresponding to the first case, and you see the right hand side is homogeneous, there is nothing else because it is a base excitation problem. So, no other force is applied on the system. On the other hand, for the second one also you can draw it very quickly, that this is the secondary mass M2. So, this is going down. So, that means the inertia force is in the reverse direction, that is M2 x2 double dot, and there is a resistive force here, that is from the K2 just opposite in direction, which is K2 star x2 minus x1. So, these these are the two components, nothing else excites the secondary mass. So, thus you can get the second equation. So, now we have both the equations with us corresponding to the displacement transmissibility. Let us now consider that what will happen if the x is x e raised to the power j omega t. Let us try to imagine, and then x1 is the displacement of m1. Let us say this is also harmonic, and that is x1 e raised to the power j omega t, and at the same frequency, and x2 as x2 e raised to the power j omega t. Now, this will not happen immediately if you give a base excitation. This will happen when the system will continue under steady state condition. So, this you have to keep in your mind that this is a steady state condition. So, under steady state condition, if I apply these things on the equations above, what will happen is that we will be having now of course, K1 plus K2 star minus M1 omega square x1 minus K2 star, and then we will be having K2 star minus M2 omega square x2 equals to K2 star x1. So, we will be getting two equations, and in these two equations we will be having no forcing function part in it, and this we are converting the ordinary differential equations by applying these conditions, we are converting it to algebraic equations. So, this is a conversion in the steady state. So, this is ODE to begin with, and this is a algebraic equation that we are getting, that is the advantage. So, it will be much easier for us to tackle the whole thing in the steady state. Okay. Now, using these 3 and 4, I can, it is just a matter of elimination, I can easily find out that what is x1 over x, right. So, if we try to do it here, that first of all x2, you need to note down that x2 is actually K2 star over K2 star minus M2 omega square, and then you use it in the first equation. So, you should be able to get a relationship now in the first equation. Now, in the first equation we have K1 plus K2 star minus M1 omega square x1, that is considering this term and K1 x1 term and M1 x1 double dot, okay, and K2 star x2 we are getting, that is considering this term. So, now let us look into the third equation then. That means the third equation will now become k 1 plus k 2 star minus m 1 omega square x 1. So, this minus, so we can keep the k 2 star times this relationship. So, this is x 2 is this times x 1. Okay. So, now x 2 I can replace this. So, that means it will become k 2 star again k 2 star times k 2 star divided by k 2 star minus m 2 omega square, and the whole thing will be with respect to x 1, that will be equal to k 1 x. So, with these things if we keep in our mind, we should be able to find out what is x 1 over x. If you just continue in this direction, as you can see that you will be having this k 2 star minus m 2 omega square, this one, and k 1 in the numerator back. So, that is what is happening here, and in the denominator it is a little bit complex, but you will be having k 2 star minus m 2 omega square square. So, that term you will be getting k 2 star minus m 2 omega square term here, and you will be having k 1 minus m 1 omega square term here. So, all these things after the algebraic manipulations will give you the final transmissibility function in this particular form. And similarly, once you do it for one case, you should be able to do it for the TR also, where which requires x 2 minus x 1. So, you already know the relationship between x 2 and x 1. So, that is why you will be able to find out x 2 minus x 1, and then you can find out x 2 minus x 1 by x, which will take up this form. One thing that we can see here is that denominator in both the cases remained unchanged, whereas the numerator will be changing. In this case, the numerator is k 1 times k 2 star minus m 2 omega square, whereas here it is k 1 m 2 omega square. So, the numerator will be changing. So, thus we should be able to find out both transmissibility as well as relative transmissibility of the system. Now that we know this, we need to do a bit of non-dimensionalization of the problem. In order to do that, some very important thing, this is important from the design point of view, that some very important non-dimensional parameters we introduce generally. The first parameter is the inertia parameter or the mass ratio, which is m 2 over m 1. That means the ratio of the secondary mass to the primary mass. We generally do not allow the secondary mass to go beyond a particular level, because then the mass penalty will be very high. So, this mu is one term that is needed, which is which actually talks about the mass penalty. Then you have the tuning ratio. Tuning ratio is having a frequency ratio omega a over omega 0, where omega 0 is actually called the locked frequency of the system. So, that means omega 0 is a non-dimensionalization with respect to a condition where you have k 1, you have m 1, and then m 2 is very rigidly connected with m 1. There is the spring stiffness here is actually k 2 star that tends to infinity. That means it is rigidly connected. So, that is why the natural frequency of this system will then become omega 0, that is what square root of k 1 over m 1 plus m 2, that is the locked frequency. Now, what is omega a? Omega a is actually the apparent natural frequency of the secondary system. That means, in that case you have actually k 1, you have m 1, and you have this k 2 star, and you have m 2, and omega a talks about square root of these k 2 at a particular frequency level. That is why it is the apparent frequency level, the stiffness of observer at frequency omega a. So, once you know the frequency, so at that particular frequency level over m 2. Now, why do you think that omega a will actually vary, and why do we need k 2 a as a function of omega a. It is because if you remember, I told you long before that the viscoelastic materials, if I plot their characteristics like omega versus their modulus of elasticity, which is actually somewhat reflected in terms of the stiffness. So, if you look at the real part of the modulus of elasticity, then low frequency is equivalent to a high temperature behavior and high frequency is equivalent to a low temperature behavior. That means, the modulus of elasticity will be low initially and then it will increase. So, that means your modulus of elasticity is a function of the frequency we are talking about. And since modulus of elasticity is a function of frequency, hence k itself, let us say if it is an axial member, if you consider that this spring is a viscoelastic spring, okay, with an axial member, then what is the k for this case? It is A E over L. So, that means k real will be actually A E real over L. Now, since E real itself is changing with respect to frequency, so this will be a function of frequency. So, that is why your k r is a function of the frequency, and that is what the tuning ratio comes into the picture. The next is the excitation frequency ratio, which is very simple. It is actually the ratio of the actual frequency where I am exciting and normalized it with respect to the locked frequency of the system. And finally, the loss factor, and that is defined as standard the difference between the imaginary part, that is what is k to I over k to r, that is what is the loss factor. Now, if you apply all these parameters, the transmissibility's non-dimensional representation will take this kind of a form, which is a complex form. That is why you need these two things in order to get the amplitude of the system. So, as you can see here that in the complex form is having this is, you may call it as n real and you may call it as n imaginary. So, this bit is n imaginary and this bit is n real, real part of the numerator. Similarly, you have the real part of the denominator, this is d real, and the imaginary part of the d imaginary. So, you can find out the non-dimensional frequency very easily once you transmissibility very easily once you know what is nr, what is n imaginary, what is dr, what is d im, because all that you will be doing is actually taking the ratio of nr square plus n imaginary square in the numerator, and in the denominator we will be having dr square plus d imaginary square, and that will be our the amplitude of this will be what our T non-dimensional will be. So, we can easily actually find out this whole non-dimensional transmissibility. Now, for certain case, let us say for two extreme cases eta 2 omega equals to 0 and eta 2 omega equals to infinity, if I try to plot them. So, how will it look like? Well, for eta 2 omega equals to 0, it would mean actually that it is like a vibration neutralizer problem, because there is no damping that is there. So, that means eta 2 omega equals to 0 would behave something like k 1 here, m 1 here, k 2 here, there is no damping there. So, that is why k 2 star I am neglecting. So, this will be eta 2 omega 0, and if eta 2 omega equals to infinity, then that means the other case where the whole system behaves like a single degree of freedom system, that is the locked frequency system. So, in that case you have k 1 here, m 1 here, and you have m 2 here, rigidly connected system. So, naturally you can see that that is the case where there is a single degree of freedom. So, there is only one peak, whereas in this extreme case you are getting two peaks to the system. Why we solve it for these two? It is because if you now look at this very carefully, you can see that there is one point of intersection here and another point of intersection here, and these 2 points are also called fixed points. And as you can see that irrespective of the frequency and the irrespective of the damping level, most importantly the eta 2 omega, whether it is 0 or infinity, the transmissibility curve has to pass through these 2 points, because all the extreme cases are covered. So, what we generally try to do is that we try to put one of the peaks to pass through one of these fixed points, because anyway the fixed point is like a hurdle that you have to cross. So, we try to put our curves like this. This is one option, or the other option is that it will go small here, but it will touch this one here, either of them. So, that means because anyway you have to cross the fixed point. So, you try to place the peaks corresponding to either of the transmissibility through these fixed points, and then under such conditions you will be able to get that what is the optimal eta 2 omega, because that has to be somewhere between the two. So, it is neither 0 nor infinity, for which eta 2 omega you will either get this configuration or get that configuration. Now, suppose I get one as eta 2 omega left, and I get another as eta 2 omega right. So, that means my best condition will be average of the two, that means half of eta 2 omega left plus eta 2 omega right. Also, I can find out that corresponding to what tuning ratios etc., this particular situation comes, and thus we can find out all the optimal values of it. I leave it to you as an exercise. Now, from here we need to go to a case which is known as active dynamic vibration absorber. So, in the passive case, at least the dynamic vibration absorber case, the most generalized case is better, because you have an additional point with you, pointer with you, which is the damping part in it. So, that is why instead of getting a good transmissibility only at a particular frequency level, to reduce that you can actually get it for a range of frequency. So, that is there in your hand. However, it is passive in nature, that means once you design it, the transmissibility curve is fixed forever. Now, suppose I do not want to do that, I want to have a more dynamic control over the transmissibility. In such a case, instead of adding a damper passive, I will be adding a feedback element like an hydraulic actuator. And if I do like that, so what will happen is that I have a K2, I have an additional contributor here, which can work like a stiffness contributor, or it can work like a like a damping contributor. So, by varying these, by tuning this Ke, I can actually cancel this effect of f bar e raised to the power j omega t. Let us look into the formulation of such a system. So, as you can see here that under such a condition, now the right hand side is not 0. So, we have m1 x1 double dot, which is the inertia force here, if you remember that this is what we have, and K1 x1 is also from here, that is the spring resistance K1 x1, and then K2, this part K2 x1 minus x2, that is the resistance that is coming from the bottom. So, that is this part, and then we have the force excitation, which is f bar e raised to the power j omega t in the right hand side here. In addition to that, we have this effect Ke, and this Ke effect is in my hand. I can choose it this way or I can choose it that way. By actually the actual expression is Ke x2, but this Ke can be positive or it can be negative. We will in fact see that what will happen to positive or a negative feedback. So, thus we can vary this direction of this additional force that will be there in our hand. Now, as far as m2 x2 goes, once again you have m2 x2 double dot, that is the inertia force, and then you have K2 K2 x2 minus x1, that is this force, that is the spring force, and an additional force which is in the right hand side, that is Ke x2. Okay, so, that also we can control the direction of it. Now, we can put x1 as x1 e raised to the power j omega t, x2 as x2 e raised to the power j omega t, just to get the steady state response, because we are converting the ODEs just like last time, we are converting the ODEs into algebraic. So, these are ODEs, right, ordinary differential equation, we are converting them to the algebraic equations. And once I do that in the steady state, I get these relationships, working on which you will get a relationship between x2 and x1, in which you can actually control x1 or x2 vice versa by controlling this gain k, and you can make it positive, make it negative, you can actually play with it. That is the advantage of active vibration control in this case. Now, in this case then we can get the first equation of motion, work on it, and this will be the final form of the first equation of motion. So, this is the steady state form of the first equation of motion. So, in the last slide we have seen the steady state form of the second equation of motion, and this is the equation 1, the first equation of motion. We can also get the steady state representation of this first equation of motion. With that, now we will be able to find out that what is x1, that is the response of the primary and subjected to a force amplitude f bar. So, this is what the expression that will come out. You can try the same thing using these last two steady state equations, and this is what is x1a, and if I put this k to be 0, this k is 0, this k is 0, this k is 0, then I get a simplified form where that active part is not there, the hydraulic control is not there. So, the first case we call it to be active, second case we call it to be passive. Now, I can make a ratio of passive and active, it will be a nice non-dimensionalization. Also, it will tell us that how much effective is the active response with respect to the passive one. So, we can find out it by comparing these two equations. You have a pretty complex equations, and that you can find out the expression of it. So, we can have x1a over x1p with us, and we can take a simple case. Let us say primary and secondary stiffness both are same, primary and secondary mass both are same. It will not happen, but it is just in terms of a kind of a simple comparison, and we put omega square as omega square over k by m. Then I can non-dimensionalize and I can get this following expression over x1a over x1p. Now, with this expression in hand, I can try with various ke over k. So, for example, I can try ke over k minus 2, then I will get this expression with us. I can try k over k as plus 2, then I get this expression with us. So, this minus 2 actually says that I have a negative feedback system, and this one actually is a positive feedback system. So, what you will see is that this expression, if you now plot this transfer function with respect to omega, you will see that this will give you a much better solution in comparison to the positive feedback. So, you can verify yourself that active vibration control with negative feedback of the displacement of the system would work much better in terms of vibration control. So, this is a special case, and when we will talk about control, I will talk more about it. This is where we will put an end. In the next lecture, we will learn about proof mass actuator and application of active dynamic vibration observers. Thank you.